Now moving into slightly longer questions that have more bits to them as much as anything else. So alcohols classified by primary, secondary, or tertiary. What's primary as applied to an alcohol? Well, it means you've got a carbon that has an OH, that's why it's an alcohol, but the carbon also has 2 hydrogens on it and 1 R group. Secondary, of course, you have 2 R groups, which I drew here in this formula as just R2, but they're not necessarily the same, and 1 hydrogen. And then a tertiary, you have no hydrogens on there, which of course significantly affects the reactivity of the alcohol group, and 3 R's that again don't have to be the same. So alcohol, you've got to have the OH, and then primary, secondary, tertiary tells you whether you have 1, 2, or 3 R groups. Structural formula name tertiary alcohol contains 5 carbons. This is done in another worksheet, so I'll just go through it quickly. First of all, the tertiary alcohol means you've got to have COH and then carbon, carbon, carbon. So of course that means that you've taken care of 4 of the carbons, so the 5th carbon will just be on one of these groups, and it doesn't matter which one is the ethyl as opposed to methyl, they're all the same. One test that will investigate whether alcohol is secondary or tertiary, include the reagents used. Well, the big one is that primary and secondary alcohols can be oxidized. Tertiary can't be under normal conditions. And if you use really forcing extreme conditions, then you smash the molecule up. So in order to distinguish whether it's secondary or tertiary, try to oxidize it. You can oxidize with one of the acidified chromiums, so either chromate here, or we could have used dichromate, going from in dichromate from orange to green, chromate going from sort of yellowy to green, or we could use the purple permanganate, acidified permanganate solution, which of course when it acts as an oxidizing agent takes the manganese down to the colorless Mn2+. See either of that, it's secondary. So staying on the theme of oxidation, we're using acidified potassium dichromate. Solution changed from orange to green. Compound Q of this formula was formed. Compound Q had no effect on Tollens reagent. Name type of reaction occurred when compound P was heated with acidified potassium dichromate. Well, first things first, 4 carbons and 1 oxygen, you would expect 10 hydrogens, so there's no double bonds, there's no rings at all in this first molecule. That tells you it must either be an alcohol or an ether, because you've got the 1 oxygen there, and that oxygen has to be single bonded to a carbon. So let's see what happens. Type of reaction occurs when P was heated with the acidified potassium dichromate. You see acidified potassium chromate, acidified potassium permanganate, basic potassium permanganate, and so on. You know those are oxidizing agents, so we're going to have oxidized P. Now, the information the lack of Tollens gives is that we look at the product C4H8O, as we said, 4 carbons expect 10 hydrogens, we've only got 8 hydrogens, so we're short a hydrogen. Seeing as how this up here didn't have any double bonds or rings, this can't have rings, therefore this must be a double bond. And seeing as how you got double bond, it's either an alkene or a carbonyl, C double bond O, an aldehyde or a ketone. After an oxidation, you expect it to be an aldehyde or a ketone. Now, aldehydes react with Tollens reagent, so therefore it's not an aldehyde. Thus, Q, compound Q here, must be a ketone. And if Q is a ketone, the way that you get a ketone via oxidation is you oxidize a secondary alcohol, so P must be a secondary alcohol. Halogen alkanes hydrolyzed when heated with aqueous sodium hydroxide. Right, equation showed hydrolysis, blah, blah, blah. So there's 3-chloro-2-methyl pentane plus sodium hydroxide. You substitute, I don't like the word hydrolyzed, I'd rather call it a substitution of the Cl by the OH, leaving you behind with Cl minus, which of course you write with the sodium because the hydroxide was introduced with the sodium. Mechanism is a substitution. It's not really a mechanism, it is a substitution reaction, but what the heck, this is A-level after all. Chemical test to show the hydrolysis reaction has occurred, include the test result expected. Well, there's 2 things you can do. You can test the organic product right here because you've made an alcohol, okay? And it is a secondary alcohol, so the OH group could be oxidized. using dichromate, which of course would go from the yellow chromate here to go from the orange to the green, or dichromate yellow to the green, or the permanganate to go from purple to colorless. So if your organic test or your organic product gives you one of these results, then you know that the reaction has happened. Easiest one is you test for the side product, because let's face it, if you wanted to make this, you don't then want to use it up testing for it. The side product is sodium chloride or chloride. Any test for chloride, bromide or iodide, add silver nitrate solution, and if you get a white precipitate, then that tells you you have AgCl in there. And the only way you'd have AgCl as the white precipitate is if you had Cl minus, and the only way you have Cl minus is if the reaction took place. Should point out that, of course, you have to neutralize this first, because sodium hydroxide is a base, and if you add in silver to sodium hydroxide, you make a white precipitate of silver hydroxide. Another question that, if you've worked through some of the other worksheets, you've seen a whole bunch. We've got a compound that is C4H7 Br, and it can be one of these three compounds where you've got a double bond in there, or it can be this compound where you have a ring. What we're looking for is a chemical test that would show the compound was either L, M, or N, and not this one. Well, of course, the obvious feature of L, M, and N is they have a carbon-carbon double bond. Test for that: bromine water or permanganate, where you see a distinct color change. Bromine water going from yellowy brown to colorless. Permanganate, where you go from purple to colorless. And neither of those tests will react with bromocyclobutane. Finally, compound is known to be one of butanol, methyl propanoic acid, and 3-hydroxybutanoic acid. So there we are, one of those. Complete the table below, because we want two chemical tests that will enable us to determine which it is. Give the reagents, observation expected for each test with a tick or a cross. So first thing I would do is I would say, hey, we've got acid groups in two of those, which we could have told from just the names, acid, acid. Test for acid groups, you can use sodium carbonate, in which case you'll get effervescent, or you can use magnesium in there, in which case you'll get effervescence for the two acid groups and nothing for the pure alcohol. Now, the next thing we can do is we can say, hey, we've got alcohols there that are oxidizable. They're both secondary alcohols, and so we can either use the dichromate or permanganate, depending what we want. Dichromate goes from orange to green. We could use chromate going from yellow to green, or permanganate goes from purple to colorless. And what we'd see is we would see these color changes for either the 2-butanol or the 3-hydroxybutanoic acid. Because of that, we would not see it for the 2-methyl propanoic acid, because this OH is not an alcohol, it is an acid OH. Final little test, if we want, is we can recognize that we have a CH3COH group, CH3COH group, which will give us a positive iodoform test. So we take the iodine, sodium hydroxide. If we have this group there, we'll get a yellow precipitate for 2-butanol or the 3-hydroxybutanoic acid, and we won't see that for the 2-methyl propanoic acid. So a nice, fun little question to end up with.